Hi, it's Mr. Baker here, and today we're going to be looking at atmospheric pressure. So we're going to do these things. We're going to describe how the pressure and density of the atmosphere changes at different altitudes, and then we're going to be able to explain using the particle model why that might be. So let's look back at how we can work out the pressure in a fluid. So this is what we've said so far, that for a column of fluid, gas or a liquid, so a fluid could be a gas or a liquid, the pressure is given by this equation here. Pressure equals height times density times gravity. We've got this diagram here, so if you've got a column of a fluid like this, of a certain height, certain density, then the pressure is given by the height times density times gravity. Now, that's okay for small heights of something, but as the height increases, then you can see with this diagram that something changes. So this is sort of a representation, a diagram of a column of air of the atmosphere. And so you can see lots of particles of air close together at the bottom near the sea level. But as that goes up, as the height increases, as the altitude increases, there's less and less particles in the same space. And that's because the density is decreasing. So at higher altitudes, there's less weight pushing down from the particles above, and so the air becomes less dense. So when we're working out the pressure, when there are large differences in height, the equation here can't be used. Okay, so the particles down the bottom are getting pushed down by all of the particles, the weight of all the particles above them. But as we increase the height, then there's going to be less particles above, so there's going to be less weight pushing down. So the density of those of the same volume of air is going to be less. So the number of particles in the same volume of air is going to be less, so the density is going to be less. So as you go up and up and up, the density decreases and decreases and decreases. Okay, so let's have a look at a kind of question that you might have. So what I'm going to do is I'm going to ask a question, then I'm going to ask you to pause it and see if you can answer the question, then I'm going to go through the answer. So first one, describe what is shown in the diagram. Okay, so have a look at the diagram, pause the video and see if you can answer the question. Okay, so what we've got in the diagram then is we've got atmospheric pressure along the x-axis, and we've got the altitude in kilometers on the y-axis. So this is our pressure, and this is like our height of our atmosphere. And then we've got a reference point here. We've got Mount Everest, which apparently is at 8.85 kilometers and at 33,000 pascals. And then we've got sea level, so obviously zero altitude, and that's 101.3 thousand pascals. So what is this diagram showing us then? So as the altitude increases, then you can see that the atmospheric pressure is getting smaller and smaller and smaller. So the diagram shows that as altitude increases, atmospheric pressure goes down. Okay, so this was just to describe, wasn't asking you to explain. So always look at these command words in these questions. Okay, so next question you might get on something like this is, from your knowledge, can you explain how the altitude affects the atmospheric pressure? Again, I'm going to ask you to pause it and then go write your answer, and I'll go through it with you. Okay, so pause it there. Okay, so can you explain how altitude affects atmospheric pressure? So from our equation, pressure equals height times density times gravity. So that's our equation for pressure in a fluid, and when we've got a column of fluid. And so from this equation, pressure is proportional to the height of the fluid above it. So as the altitude increases, the height of the air above it is less. Okay, so pressure is proportional to the height of the fluid. So if we're looking at a column of air above this point here, we've got all of that air above that point. So we've got a large amount of air above, so it's going to have a large pressure at that point. If we looked at a column of air on the top of Mount Everest, it's going to be a smaller height above Mount Everest of air, and so because of that it's going to have a smaller pressure. And as we increase the height, we just look at a point, the air above that point is going to be less and less and less, so the pressure is going to be less. Okay, next one. So would you expect a curved line, and can you explain why or why not? Okay, pause it there. Okay, so you maybe wouldn't expect a curved line, I think. If you are just looking at the equation, we've said that the pressure is equal to the density times the height times the gravitational field. And so if the density of the air remains constant, then you would probably expect a straight line for that. So that leads on then. What does the curve suggest? So can you explain why it's a curve, basically? Okay, so pause it there. Okay, so the curve suggests that the density of the atmosphere decreases as the altitude increases. So it's not a straight line, and we'd expect it to be a straight line, but it's not, and that suggests that the density is decreasing as the altitude increases as well. Okay, so that's atmospheric pressure. We've looked at how the pressure and density of the atmosphere change at different altitudes. We've looked at the particle model, and we've explained why it might be difficult to calculate pressure over a large change in height using the equation that we've used. So that's this lesson over. Well done, thank you very much, and I'll see you next time.